first, sorry.
Okay, so the last time, many years ago when we met, we were talking about integrality. Let me give you kind of a sort of a warm up. I'll call this an unnamed box. Let R be ring one and P extension ring. So this will lay out me. R is contained in T. If P is a finitely generated and P is infinite. So um, and consider uh, or uh, uh, let me state this. Well, let x1, x2, xn, there you go. That's what I want to do that. Be a generating cell for the module. P over R. So this is actually, I mean, I guess I'm probably, this is kind of silly thing to do, we're going to go into the exercise again, but I claim xi, one of these generators, is infinite. And how will we do this?
Use that characterization for integrality in terms of finitely generated or so long.
Okay. Or you could also consider powers of xi, if you will, because every power of xi must be an R linear combination of these guys, and you get the same kind of equation that you did. And once that is taken care of, since sums and products of integral elements are integral, this will do it. Because of course, every element in T is a R linear combination of these guys. If all the xi's are integral, then every Ri times xi is integral because of the product thing, and then sums as well. So if you have a finitely generated, so if you have a ring that's also a finitely generated R module, that ring extension has to be integral. Of course, it's very, let me cook up a quick example. is in prime. This is not a finitely generated Z-model. I'll leave that as an exercise, but clearly you can see there's no finitely generated Z-model, but it is an interval extension. And again, that's an application of the stuff we're taking. It's fairly clear that all these elements here that we're adjoining are integral, are they not, right? Because the square of them, that in fact, in general satisfies, or it's a rooted polynomial x squared minus pn. And of course, an arbitrary element in this ring is sort of polynomials and products of these. But of course, products of integral elements are integral, and so there we have it. Okay. Okay, so I like to call this theorem the sort of the no new units theorem, but let's be careful with the way I put this. Let R and T right. Here, R and R is a non-unit, then R is a non-unit. So, in particular, this is what, when you take the units in T and you intersect with R, you get the units of R. So in other words, let me, I call this the no new units theorem. Of course, there can be lots of new units in T, right? But none of them can come from R. Anything that has non-unit status in R remains non-unit in an integral extension. So in particular, this sort of makes this sort of diametrically opposed to localizations in a certain sense, right? Because what happens in a localization, you grab a set S and you turn all those things into denominators, right? So there's lots of new units. In fact, everything in S in a localization becomes a unit. Everything in the multiplicative set in R becomes a unit localization, right? But sort of the opposite is true here. Nothing becomes a unit unless it was already a unit. So let's prove this. Let's suppose that R is a non-unit in R. And there exists a key in R such that RT is 1, and I do mean a P and a T. Okay, so suppose we have a non-unit R that becomes a unit upstairs. We're going to get a contradiction here. So what do we know about T? Well, since T is integral, there exists Ri in R such that T to the n, Rn minus 1, Tn minus 1 plus R1T plus R0 is equal to 0. Everybody okay with that? So anybody see what we can do here? I'm gonna multiply both sides of this equation by r to the nth power. Well, so let me, for dramatic purposes, multiply this by r to the n. And what that's gonna come, this is gonna be RT to the n plus Rn minus one, RT n minus one. Only need n minus one powers bar there. Plus R1, R to the n minus one, RT plus R to the n, R0. It's equal to 0. Right? But of course, the RT bit is one, right? By assumption. So what I get is 1 is equal to, notice this is R times negative Rn minus 1. And we go minus R1, R to the n minus 2, 1, minus Rn minus 1, R0. And there we go. And notice that this is an element of R. Therefore, R is a unit in R, and we're done. And notice, with regard to my remark about the units, notice that the units of R is contained in the units of T and R. Right, because by definition, anything here is in R, and of course, anything that has an inverse in R certainly has an inverse in T, because it just carries inverse. And the other containment then T is in R, but since T is in UR, T is in UR. And in fact, it turns out it's, especially if you look at things like factorization, extensions more generally than integral that satisfy this, the units of T intersect R's units of R, can be very important. Okay. Any questions on that? Okay, here's one that's not difficult to prove, and almost, I mean, when you prove this, it almost seems a little bit silly. But it's surprisingly useful, and we're going to use it later, and in stronger contexts too. So I almost want to call this, instead of a proposition, I'm going to call this like almost an observation. Right. Let R be commutative ring with identity. And one, and U, an invertible element of a ring containing R. In other words, in particular, if U is in R, you don't want it to be a zero divisor. Example, then U inverse is integral over R if and only if U inverse is in R. If and only if U inverse is an element of R, U, the smallest ring containing both R and U. Well, I mean, this, you can just get on your horse and ride this one. Let U inverse. Suppose that U inverse is integral. Well, so that means the U inverse is, a root of some polynomial. That's one inverse, n minus one. U inverse. So actually, it might be clearer for me to do this. U to the minus n. All one, U minus one. Now, multiply both sides of this equation by U to the n minus one. Where's my magic orange chalk? Multiply both sides by that, and I get U inverse plus Rn minus one plus Rn minus two U plus R1 U n minus two plus R0 U n minus one is zero. Right? And this chunk right here is then RU, because it's polynomial in U, if you will. So take this over to the other side and you get U inverse is in RU. Right? And this thing is invertible. So for example, if U inverse is in RU, then U inverse is equal to, let's say, Rn minus one plus Rn minus two U plus R1 U n minus two plus R0 U n minus one. Take it over and multiply by U to the one minus n. Right. So same stuff. Just okay. So this is this will come up later. This is kind of an important thing. U inverse is integral over R if and only if U inverse is in RU. This is actually, even though it's a simple observation, is a useful useful piece of information. Here is a corollary to all this. So, corollary. Let R be a domain and F any field containing R. And F a field containing R. If F is integral over R, then what can we conclude?
Art.
That is correct. So really what this says is if you're talking about integrality, if a field is integral over you, then you're back to field theory, Galois theory. So if you have an integral extension of, if you have a field that's integral over an integral domain, that domain has to be a field. And this is a corollary to either of these things. Proof. Notice that R is in UF intersect R with just UR. So R is the field. You can also couch it in terms of the previous proposition as well. That's pretty quick, isn't it? And that's kind of a nice result. I mean, if I just gave it to you without any of this context, just kind of naked prove this, then I think you have to think about it a little bit. You end up sort of reconstructing some of this other stuff. Right. So, any questions? Okay. So, theorem. This is going to connect up to what I talked about a little bit earlier today. Let T be a commutative algebra over R. Well, let R be a commutative frame. And T a commutative R algebra. The following statements are equivalent. T is a finitely generated R module. Two, T is finitely generated as a ring over R, and T is integral over R. And T is okay, so we talked about a little bit of this earlier. So when we look at one implies two, we've kind of got that already. One implies two. We've already talked earlier today about if you're a finitely generated R module, then you're integral. Right, so we've got that. And if you're finitely generated as an R module, you have to be finitely generated as a ring. Just take your finite number of generators from the R module and let them do their thing as a ring. So that's not a problem. If you have integral and T is finitely generated as a ring, then you have it's also finitely generated as an R module. Notice this does not apply to that second example I gave you where you had Z adjoined with square root of 2, square root of 3, square root of 5 forever and ever, because that's not even finitely generated as a ring. So suppose that we have that T is finitely generated as a ring and T is also integral. So for this implication, T is generated as a ring over R by T1, T2, Tn. All right, so now let's say this is T is the smallest ring containing R and these N generators. And I like writing in this form because this sort of reveals perhaps what the proof's gonna be. What is a typical element of this? I mean, this isn't really a polynomial ring because these elements might have algebraic relations, but you can think of everything as written in that form, right? Sort of sums of monomials of, products of powers of these things, right? So what is going to be the key? The key to this is a typical element of this is a cluster of monomials of products of powers of these TIs, right? But the ring is integral. So once you reach a certain power for every TI, then it's repeating itself. And so let me kind of write this down. Suppose the minimal polynomial polynomial for TI is degree n spi. So T can be generated over R as a module by the elements T1, A1, T2, A2, Tn, An, with each AI between 0 and Ni minus 1. And that's a lot of elements, but it's certainly many of them, right? Because once you hit the magic, say that An is actually, I'm sorry about the W sub n there. But anyway, say that this is N sub n, right? Then of course this thing can be rewritten as lower powers of Tn, and you can redistribute it back to the other generating monomials. So you generate this by, I guess you get what, the product as a module, so you get 1, so these can all go between 0 and 1, so I guess you get the product of n I. Yeah, sorry about that. Oh. Yeah, that's right, because you start at 0, start counting at 0. Okay, again, notice that all this stuff about no new units, everything that's non-unit stays a unit. This should be contrasted with localization quite a bit. Let me give you another result that we'll be using when we get to valuation domains for sure. And if you had 8520, you saw a similar result, probably in a more specific context. So let R be a collection of domains. all contained in the one. Right, so this is, T is just some master domain that contains all of these. If each Ri is integrally closed, then so is the intersection. Let me remind you, what it means to be integrally closed. Integrally closed means that everything in the quotient field that's integral over Ri is already there, right? It's already in there. Okay, how we prove this? So we know what K I, the this quotient field R I and F of the quotient field okay. I'm not too sure, I'm gonna need that notation, but whatever. Okay, so let X be in the intersection of Ri. I'm sorry, that's not what I want to do. Let X be integral, there we go, over so X is an element that is integral over this, and
Because it lives in the intersection of the KI, right?
and X is in quotient field. Hold on. Yeah, you're right, not just integral, but it's gotta be in the quotient field. So, of course, my goal is only to show that this is integral over R. What do I know? I know it's in the quotient field of all those Ri's. Right? So notice that for every I in this index set, X is in well, so X is in the intersection of all these KI's. So for all this X. X is integral over then X is integral over K I. I'm sorry. Right here. Since X is integral over. So since X is integral over the intersection over R. which is contained in Ri. X is integral over Ri. And is in Ki. So X is in Ri, and this holds for all I in limits. Therefore, X is in R, it's the intersection. So this is a very important result, because if you have a collection of elements, or if you've got a collection of domains that are closed, so is their intersection. So for example, if you intersect a whole bunch of collections of UFDs, and if you're a number theory fan, there's a lot of those out there. If you intersect those, you may not get a UFD, but you will get something that's interplayed closed. Okay, so in this one, this was a big one. I want you guys to help me with this theorem. 3-1. Let R be a domain then this actually very fundamental. Sorry. What do I mean by this notation here, max spec R? So let me take a little aside here. A little notation. If you ever see the notation spec R, spectrum R, this is the collection of P and R, such as P. So spec R is just the collection of prime ideas. Max spec R is the collection of maximal ideas. So what this result says is R is the intersection of R localized at all maximal ideals, right? So for example, here's a concrete example. If you look at the integers, say, the maximal ideals are all generated by non-zero primes, right? So you've got like Z localized at 2, Z localized at 3, Z localized at 5. If you intersect all those localizations, you'll get Z. And actually, you don't even have to intersect all of them. All you have to do is intersect infinitely many of them, and you'll get Z, and that'll be good enough. But this actually always holds. So let's try to prove this. One of the directions is easier. This is the easier direction. So why is it true that R is contained and R localized in? Well, what you can do is you can identify R with R over 1, which is an R over M, R localized in for all. Think of every R as R over 1. This is certainly in every. So that one's fairly straightforward. The tricky part is the other direction, right? Why is it the case that y can have
So normally when we do localizations, we set up like this equivalence relation and all that. But in this case, are we really thinking of these as being contained in the quotient field of R?
That's exactly right, yeah, that's why I like domain here, right, because it's, we don't have to worry about that crazy zero divisor stuff or any of that. And also, we have an identity, right? Why is this the case?
We take an element that's in the fraction field but not in R, then it's not invertible. And so it has to be contained, but its inverse, which is in R, has to be contained in some.
Well, so,
One over B, yes, sometimes.
yes, as Bradley points out, so suppose we have X is R over M, it's an R over M for every M. We can write X as a fraction, A over B, with A and B. Now, I'm gonna form the following ideal. I'm gonna say, I want the R and R, such that R is. So I will look at this ideal here. This is a collection of everything in R that throws A into B, right? So in other words, everything that you can multiply this fraction from in R that makes that numerator a multiple of the denominator, right? That's essentially it. Now, by the way, what goal do I want here? So goal, I hope, so this maybe I should write which was I is equal to R. Right?
We can expand.
Because if I is equal to R, that means one is in here, which means that whenever I multiply A times one, it's a multiple B, which of course forces this to be an R. And that would mean that this X is in R, and I get the containment element. Everybody okay with that? Okay, so now that I have my goal, I mean, I really want this to be the whole ring so that one's in there and that forces this thing to be an R. And I think that writing that goal down there maybe clarifies the strategy. So what should we do then?
Assume it's not, and then expand I to a maximal, I think. Okay.
If I is not equal to R, then there exists maximal ideal. Maybe I'll write this one a little bit different description. M such that I is a in M, right? And so, notice that is in R localized in M. Then we have that So A over B is in this particular localization. So A over B should be written as C over S, where S is not in script M. Right? And so, right. So AS equals BC. And so, therefore, S is in I by definition, because S tosses A into the ideal generated by B, and I is contained in M. Because this is not an M, this is an M. Therefore, the intersection of R and M is contained in R, and we have equality. This is a very fundamental theorem here. Let me give you another, I contrasted, so you guys, maybe want to think about this. Yeah, because this would be a good place to start. Or maybe I can get you started on it. Localization is very compatible with integrality in the following sense. I mean, there are different operations, of course, but give you this theorem here. If R is integrally closed, opposition. If R is integrally closed, and since I'm talking about integrally closed, implicitly I'm talking about the domain, because I have to have a quotient field. If R is integrally closed, and S in R is a multiplicatively closed set, and I'm going to say not containing 0. Safe side, then R localized isn't closed. So this is kind of a nifty theorem here. If you've got a domain that's integrally closed, and you have any multiplicatively closed set, this creates an overring. So this is actually between R and RS, but this new overring is also integrally closed. You don't get any new integral elements out of this. We will discuss the proof of this next time. Any questions?
So far as a PID, then every overring is integrally closed.
Yes, and in fact, there's a much more general thing that I'll tell you later. It turns out that if you have any proof for domain, which is much more general than a PID, any overrings are closed. Okay, other questions? That's a nice observation. All right, we will see you on whatever day comes next.